So that's conservation of mass. And we're going to talk about momentum next, but first we need to talk about another identity. So in the previous one, our control volume was fixed, but what if it weren't? If we had a control volume that, say that had a volume V of t, a surface S of t, right? And over some time, we change it such that it's, at V plus delta t, S t plus delta t. So at some later time, we've changed the control volume, and we want to know what happens to some quantity inside it. And the quantity is arbitrary at this point. I'm just calling it A, but it could be energy, it could be momentum. Energy is a scalar, momentum is a vector. So I'm not going to make that specification right this second. I'm just going to say A, and I try to write it like a script A, just to be different, because just to point out, it's just some arbitrary quantity, right? And I want to investigate how A changes with a change in control volume. So in other words, I want to know what d dt rho A with a change in control volume might be. So before, if the volume isn't changing, we saw, you can just move the differential operator inside, right? But we can't do that here because the volume might be changing. Okay. So in words, what we're interested in is, sort of the time rate of change of A, time rate of change of A inside a changing V. And what that has to equal is the sort of instantaneous change in A. So what I mean by instantaneous is like, at a constant V plus the flux of A, right? So if I'm changing the control volume, there may be something internal to the control volume that's making A increase, right? It could be internal energy or something's going up. That's internal to A, but I'm changing the control volume. There also might be some flux, right, across it. Okay. And so if we write sort of in equations what I wrote in words, we have d dt, and I'll try to keep the t there so you know that this is that's equal to the instantaneous change in A. That's d dt. Well, I'll go ahead and move that inside. Plus the flux of A. Yes, okay. So I'm going to start manipulating this equation then. The first thing I'm going to do is use the divergence theorem to convert this surface integral to the volume integral, right? So this guy is going to become that guy. All right. And so then I'm just on this first term, I'm just going to apply the chain rule. I'm going to apply the chain rule to this guy, and I'm going to apply the chain rule to that guy. and I'm going to write down what the long written out form is. Okay, so I have A d dt rho plus rho d dt A plus, now when I apply the chain rule on this divergence operator, I'm going to keep rho v grouped. So I'm going to, there's three terms there, right? So I'm going to group rho v and act like it's one term and keep A as one term and apply the chain rule that way. Right? So if I do that, then I get A divergence rho v plus rho v grad A. All right. And I'm just going to write this a little bit different. I'm not going to change the equation anyway, except I'm just going to do a little factoring. Okay, so we've manipulated our equation. What is this? It's conservation of mass, right? And that's equal to 0. What is this? It's the material time derivative, right? Okay. So with those two things, we had that ddt of v that changes is equal to rho a dv, right? That's what we're interested in, finding out what that's equal to, and it's equal to rho dA dt dv, right? So for a changing volume, the time rate of change of this guy is equal to the material time derivative of A. So this thing has a name I'm sure you've heard before. Anybody know? It's called Reynolds transport theorem. Never heard of that? Usually, like in an undergraduate fluid mechanics class, it's, you just present it. It's not derived like we just did.